Alright, let's take a look at a ray optics problem. So this one says that we have a 5 centimeter tall candle which is placed 15 centimeters in front of a converging lens that has a focal length of 20 centimeters. We want to determine the image distance and the image height, and we want to do that using actually two methods. First one is using ray tracing. The second method is going to be using the thin lens equation. Alright, so let's get started with the first method, the ray tracing method. For that one, we have to draw the lens. So we're going to draw in this case, a converging lens. And we need to draw a line that goes through the middle of the lens. That's the optical axis. We're going to choose a scale here. I chose 3 squares horizontally. 3 squares represent a distance of 5 centimeters. So notice that also the focal points have been indicated here. The focal points of the lens. A lens has always 2 focal points, one on each side. So each one a distance 20 centimeters from the lens. One on the left, one on the right. And the other thing that I'm indicating here is the candle. There's a little candle here in orange. That is, the candle is supposed to be located at 15 centimeters away from the lens. So I just drew it on the left. You could have done it on the right. I put my candle on the left of the lens. And the height of the candle, I chose it to be 1.5 squares, which is going to represent a vertical distance of 5 centimeters. Alright, so with this, now we start the ray tracing method, which involves drawing what I call the 3 principal rays. So the 3 principal rays are 3 rays that are easy to figure out what they do. When they leave the object and they interact with the lens, it's easy to figure out what those rays are going to do. So one of them is the light ray that goes parallel to the optical axis. So it leaves we're going to assume that the light rays are leaving the top of the candle. So we're going to find out where the top of the candle is. The bottom of the candle is going to be on the optical axis. But with the ray tracing, we're going to figure out where the top of the candle is. So one of the rays is going to be parallel to the optical axis, like I said. So that light ray, we know what is going to happen to it, because the converging lens is going to send that light ray straight to the focal point on the other side. That's what any converging lens would do with a ray that is parallel to the optical axis. So that's one of them. Another one of the principal light rays is the light ray that either crosses a focal point on one side or seems to have come from the focal point of the lens. So in this case, a light ray that leaves the top of the candle in the direction indicated there, which means that when it hits the lens, it seems to have been coming from the focal point. That light ray is going to be taken by, or it's going to be deflected by the lens, and the lens is going to turn it parallel to the optical axis. Okay, so that's the second principal light ray. With these 2 principal light rays, you can already determine where the image of the candle is going to be. For an observer that's on the right of the lens, these light rays seem to be coming from a common point. If you project them back, if you trace them back, the 2 light rays are going to be intersecting each other at some point down the optical axis, and that the point where they intersect is going to be the image of the candle. Right? We can also check our work, because there is a third principal light ray that we can draw. Is the principal light ray that goes through the center of the lens, because any light ray that goes through the center of a lens is not affected by the lens. It goes through without changing direction. So again, if we trace back this light ray, we should find that it intersects the other 2 light rays at some point down the optical axis, and this is the location of the image of the candle in this case. Alright, now all we have to do is use the scale that we have in the horizontal axis to figure out where the location of the candle is. So this is going to be 60 centimeters to the left of the lens, approximately 60 centimeters to the left of the lens. The other thing that we can figure out is what's the height of the image of the candle. So using the vertical scale that we set up, the candle's height is 5. You can see that the candle seems to be 4 times as big the image of the candle seems to be 4 times as big as the candle, so that gives us 20 centimeters for the height of the image. So the final numbers here are going to be the distance to the image is minus 60. Remember that that minus is important because the image is located upstream from the lens, and any image upstream from the lens, the distance counts as a negative number. If the image had been on the right side of the lens, then that would have been a positive distance to the image. So this is a virtual image. Virtual images have a negative distance to the image. That's what we got here. And the height of the image, as we said, is going to be 20 centimeters, or approximately 20 centimeters. When you're doing ray tracing, your answers are not going to be perfectly accurate, because when you're drawing lines and finding the intersection tends to not be very precise, but you can get a ballpark estimate of where the image and what the height of the image is going to be. Here I was very careful about drawing the lines, so that's we're going to get a result that is pretty accurate, as you're going to see when we use the thin lens equation. So we're done with the ray tracing. Let's go with the second method, which is the thin lens equation. So the thin lens equation tells us that we can calculate the location of an image, for example, using the equation 1 over f equals 1 over the distance to the image plus 1 over the distance to the object. In this case, the object is the candle, the image is the image of the candle, which we're trying to figure out where it is using this equation. So we have to replace for the focal length of this lens, we replace 20. It's a positive focal length of 20. Distance to the image, 1 over the distance to the image, and we're adding 1 over the distance to the object. So that's where the candle is located, which is 15 centimeters. So from this equation we can solve for the distance to the image, a little bit of algebra there, and the answer is negative 60 centimeters, which is, as you can see, coincides with the answer that we got using ray tracing. The second thing that we need to calculate is the size of the image, the height of the image. So the height of the image, there is an equation that tells us that the magnification of a lens is the negative of the distance to the image divided by the distance to the object. So we have a distance to the image of minus 60. We just calculated that. The distance to the object is 15. So negative 60 divided by 15 gives us positive 60 divided by 15. The answer is the magnification for this situation is going to be 4. The magnification being 4 means that the height of the image is 4 times the height of the object. So since the height of the object is 5 centimeters and the magnification is 4, we get a height of the image of 20 centimeters. Alright, clearly the answers match using either one of the methods. Alright, I hope that was clear, and I'll see you in the next one.